In the last lecture, we defined a metric on the field of complex numbers. The metric was defined using an absolute value, which was a natural extension of the notion of absolute value on the field of real numbers. The absolute value turned out to be the square root of the field norm, and we remarked that because of this, it doesn't matter which copy of the complex field that we work on. The analysis will be consistent. Let's start by recalling the metric that we defined. Recall that the metric defined on C is given by d of z comma w is defined to be the absolute value of z minus w for z and w in C. So in this lecture, we will do a quick recap of the familiar topological notions on the complex plane. This is the material will be something which you would have already seen in multivariate real analysis course. Nevertheless, let's do a quick recap. The intention is also to set the notations for the rest of this course. So the first thing is to describe balls in C with respect to this metric. We shall denote for a point z0 in C and R positive, we shall denote the ball of radius R around z0 to be dz0 R. So recall that dz0 R is the set of all z in C such that the distance of z to z0 is less than R. So the d here is actually for disk. So balls in C are also called disks. That's the reason why we have used the word d for the balls. If we are to work with a general metric space, which we will do sometimes in this lecture itself, we will use the word B instead of capital B instead of capital D. It should mean the same thing. Okay, let's now define or recall the definition of what is the meaning of a set being open in a given topological space. So a subset D contained in C is said to be open if for every z in D there exists some positive number R, real number R, such that the ball of the disk of radius R around Z is contained in D. This is another way of saying that Z is an interior point. So if every point in D is an interior point, if we can find some disk of radius R around the point Z which is sitting inside D, then we say that D is an open set. And as a complementary notion, we will also be able to define what a closed set is. A subset F contained in C is said to be closed if C, the complement of F, C minus F, is open in C. So there is an alternate way of defining closed sets, namely as a subset which contains all its limit points. So let me recall what a limit point is. We say that a point x in C is a limit point of, this is the definition of limit point of subset D contained in C if every neighborhood of the point contains a point of D other than X itself. If for every epsilon positive dz epsilon intersected with U contains a point other than Z. Oh, we started off with X, so maybe I should change it to Z here. So a point Z is a limit point if it satisfies the condition that for every neighborhood, every disk of any radius, if you intersect it with D, I'm using a different notation here. It's not U, it's D. The subset, it's a limit point of D if every neighborhood of Z intersects D at a point other than Z. In a metric space, this is also the same as demanding that you have a sequence in D converging to Z, where the sequence consists of points other than Z. And I will leave it as an exercise for you to check that a subset F contained in C is closed if and only if it contains all its limit points. I'm leaving it as an exercise. These are notions which I'm sure you would have seen. If not, I'll refer you to Rudin's book, which contains most of these results. Okay, so that's the definition of an open set and a closed set. The open sets satisfy certain properties, certain conditions. So some properties of open sets. The first one which I would like to highlight is that C and the empty set both are open sets. C and the empty set, which I am denoting by phi. Let me tell this once. The empty set are open subsets of C. Any finite intersection of open sets is again an open set. These are things which can be verified. The first condition is very easily verified if D1, maybe I should use omega 1, omega 2 up to omega n, finitely many of them are open sets in C, then so is omega 1 union is anyway there up to omega n, intersection of omega 1 up to omega n is also an open set. All finite intersections of open sets is again an open set. Again, I will not prove this, it's an easy check. You should sit down and work it out if you have not seen it before. And finally, any arbitrary union of open sets will again be an open set. So if omega alpha, where alpha is indexed by some arbitrary set, is a collection of open sets, in C, then so is, then union of omega alpha is open in C. And because it's satisfying these conditions, we commonly say that this forms a topology on the complex plane. This is commonly referred, these properties are commonly, let me not say referred to, these conditions are what makes the collection of open sets in the complex plane as a topology on the complex plane. So let me just rephrase it and say that the collection of all open sets on C form what is called as a topology on C. So our goal would be to work with this particular topology. This topology meaning that the collection of open sets which are defined using this particular metric. Okay, I would also like to introduce a few few other notions which we will encounter very frequently. The first one being that of the interior and of the closure. So let D be a subset, an arbitrary subset of C. We define the interior of D to be the union of all open sets in C which are contained in D. So let me define it, let me write it down. The interior of D is the, let me just write it in notations, is defined as, so sometimes also denoted with a circle on top. This is defined as the union over all omega, such that omega is contained in D and omega is open in C. So you look at the union over all such open sets which are contained in D, whatever we get is called the interior of D. And along the same, in a similar manner, we can talk about the closure of a given set. So let F, again, let D be, we define the closure of D to be the set, and it's commonly denoted by putting a bar on top. D bar is defined to be the intersection of all F, such that F is something which contains D and F is closed in C. So here in this first case, which I am now underlining in green by the observation which I made earlier, it's clear that it's going to be an open set, because all arbitrary union of open sets is again going to be an open set. Using De Morgan's law, you can check that the same thing translates to saying that the arbitrary intersection of closed sets will again be a closed set. So this D bar is now a closed set. The closure of D is a closed set. So the interior is in some sense the biggest open set sitting inside our given set D, and D bar, the closure of D, is in some sense the smallest closed set which contains our given set D. Okay, another notion which we will need is that of denseness. So let continuing the setup we were in, we considered a D which was contained in C, right? So let E be contained in D be such that the let E be contained in D be a subset. We say that E is dense in D if the closure of E in D is D. So I'll be a bit careful when I say this. We are taking the closure of E in D. So what does it mean to say that we are looking at the closure of E in D? In this context, in the complex plane, we can just say that it is going to be the closure of E in C intersected with D. But usually, when you take a subset D of a metric space, we can borrow or restrict the metric to this subset D, and with that restricted metric, D turns out to be a metric space. We can talk about balls in D, we can talk about open sets and closed sets in D. Basically, we can talk about the topology on D. This closure of E is with respect to the topology in D, which is obtained using the restricted metric. So let me just say that this is with respect to the collection of open and closed sets in D with metric obtained, with metric on D obtained by restricting the metric on C to D. Okay. Okay, next is the notion of a sequence converging, which I'll not spend too much time. It's just the same thing, sequence Zn in C is said to converge to Z if the sequence of real numbers Zn minus Z converges to 0 as n goes to infinity. And a function f from omega to C, where omega is some open subset of is said to be continuous. We actually don't need to impose the restriction of omega being open, but nevertheless, let me just put it that way, is said to be continuous if f inverse of D is open in omega. The condition that omega is open in C is going to help us not worry about whether it is open in omega or whether it is open in D, but nevertheless, let me put it this way. F inverse of D is open in omega whenever T is open in C. This is the same as saying that if there is a sequence Zn in omega which converges to Z in omega, then f of Zn converges to f of Z. Okay, these are the usual notions which you are familiar with. Let me not spend more time on that. Let me just make an observation that the addition operation on the field of complex numbers is a continuous operation. So this and the multiplication operation from C cross C to C are continuous. So this, what is the meaning of this being continuous? Here on C cross C, you look at open sets consisting of the collection of, the topology generated by all collections of the type U cross V. So maybe I'll not elaborate too much on this. Let me just leave it at this and say that these two operations are continuous. And this is the same as telling that limit n going to infinity of Zn plus Wn is equal to limit of Zn plus the limit of Wn, where Zn and Wn are sequences in field of complex numbers. And this is again saying that Zn times Wn is the same as limit n going to infinity of Zn times limit of n going to infinity from time of Wn. So I didn't write that these two operations are continuous, but this is effectively telling us that the operation of addition and multiplication are continuous in the product tuples. This can be checked by considering the triangle inequality and the fact that the absolute value of Z times W is absolute value of Z times the absolute value of W. So using that, this can be checked. Let us next notice or observe that just like R2 with respect to the standard metric, C is also, actually the balls are the same. So if you already have seen the fact that R2 is complete with respect to the standard metric, what we are going to check next is redundant. But nevertheless, let's check explicitly that our complex plane is complete with respect to this particular metric. But before that, maybe I should also note one more thing. Limit of n going to infinity of zn bar. This is going to be equal to limit n going to infinity zn bar. The conjugate, the limit of a sequence of conjugates is going to be the conjugate of the limit. This is basically telling us that the operation of conjugation is a continuous operation. And this follows from, let me just say that this is because the absolute value of z bar is the same as the absolute value of z. Yeah. Okay, now let's take the next first steps in showing that C is complete. We'll just use the fact that R is complete to establish that C is also complete. And in order to do that, what would be the first step? The first step would be to observe that if Z is equal to A plus IB, recall that the absolute value of Z is just A square plus B square to the power 1 by 2. And this is going to manifest in the following inequality. Mod A, in fact mod A and mod B. So let me just write mod A and mod B, both are less than or equal to A square plus B square to the power 1 by 2, which is less than or equal to mod of A plus mod of B. The first one, well, these are straightforward inequalities. Let me not spend too much time behind this. This basically tells us that the absolute value of real part of Zn and the absolute value of the imaginary part of Zn is less than or equal to the absolute value of Z. Notice that the left hand side actually consists of real numbers. Z is a complex number. Again, right hand side tells us that this is less than the absolute value of Zn plus the absolute value of the real part of Zn and the added to the absolute value of the imaginary part of Zn. Okay, what does this manifest as? Where is the n coming from? N is only going to come. I'm writing it before it's coming into the story. Yeah, so these are the inequalities we can talk about complex number Z. Now, because of these inequalities, if Zn is a sequence of complex numbers which converges to Z, then we immediately have that real part of Zn converges to the real part of Z. And we also have, so this is an implication we also have one more implication, which is basically the imaginary part of Zn converges to the imaginary part of Z. This is coming from this inequality. And this inequality tells us that if real part of Zn and imaginary part of Zn simultaneously converge to real part of Z and imaginary part of Z, then Zn converges to Z. So if Z in C be such that real part of Zn converges to real part of Z and simultaneously the imaginary part of Zn converges to the imaginary part of Z, then Zn converges to Z. I'll just write it down as just a corollary for you to finally verify that this tells us that the field of complex numbers is complete. C is complete with respect to the metric defined above. We have to crucially use the fact that R is complete. So if Zn is a Cauchy sequence, so what does it mean to say that a metric space is complete? It manifests in proving that if you take any Cauchy sequence, then we have a limit, and that's precisely what we will be doing. If Zn is a Cauchy sequence, then the above observations tell us that the real numbers real part of Zn and the real numbers imaginary part of Zn, both are Cauchy. And this the completeness of R tells us that hence there exists A comma B such that real part of Zn converges to A and imaginary part of Zn converges to B. Let Z be equal to A plus I. Then the above observation tells again that then Zn converges to Z. Hence, every Cauchy sequence has a limit. Therefore, C is complete. That was actually a straightforward observation using the fact that R is complete. Let us next discuss the notion of connectedness. Connectedness is a very crucial idea or notion which we should be familiar with, because we will be mostly interested in working on connected open sets in C. So, understanding connectedness is crucial. Let's do a recap of the notion of connectedness on C. So, what is the definition of a metric space? So, we will do one thing in this section. In the definitions involving connectedness, we will work on general metric spaces rather than working just on C. Okay, so let X comma D be a metric space. We will talk about connectedness on metric spaces, and then we will give a characterization of what is the meaning of connectedness in the setting of the complex plane. So, we will come to that in a systematic manner. To talk about connectedness in a metric space, we will first have to define what is meant by a separation of a metric space. So, we define, or we say that the metric space X, so I'll do this abuse of notation from now, the metric space X. When I say metric space X, there is an underlying distance function involved or the metric involved, which I will suppress, but there is always that metric at the back. We say that a metric space is separated if there exist disjoint, non-empty, open subsets of X such that X is equal to, okay, subsets, let's give it some name, U comma V. U and V of X such that X is equal to U union V. You can get hold of two open sets which are disjoint, which are non-empty, and open subsets, which gives us the entire metric space when we look at the union, then that is called a separation. So, for example, if you look at the complex plane, let's consider a ball of radius 1 around 0 and maybe a ball of radius 1 around, say, the point 4. Okay, so for example, X be equal to D01 union D0 D41 in C, and let's use the metric on C to restrict it to X and define a metric on X. Then U is equal to D01 and V is equal to D41 is a separation. In fact, I would say this: if we had taken X to be the closed disks D01 bar and D41 bar, and look at X, a new metric space X prime to be, say, D01 bar union D41 bar, then again U equal to D01 bar is an open set in X, and V equal to D41 bar is an open set in X, and the union will give us X. So that's something which you should notice. Let me give that as an example. Let X prime now be equal to D01 bar. So I'm putting this as a closure in C, but you should check that this is exactly the same as the set of all Z, such that mod Z is less than or equal to 1. This union D41 bar, this is the set of all Z, such that mod Z minus 4 is absolute value of Z minus 4 is less than 1. So basically this is in this picture. When we considered X, we were not looking at the boundary, which is here the unit circle and the circle of radius 1 around 4. These were not considered when we considered X, but when we are considering X prime, that set is also part of it. And you should sit down and check that with the metric borrowed from C, D01 bar is open in X prime, and D41 bar is open in X prime. So these are not open sets in C, but these are open sets in X prime in the subspace topology. And further, this is a separation of X prime. So both X and X prime are examples here of metric spaces which are not connected. Oh, I didn't define connected, so let me define what connected is. We say that a metric space is connected if there does not exist a separation of X. So there is absolutely no separation that you can find of X. And if that is the situation, we then say that our metric space is connected. There is an alternate way of saying this. X is connected. There is a, let me reformulate it. X is connected if and only if X does not contain a proper subset meaning that it is non-empty and its complement is also non-empty. A proper subset of X which is both open and closed simultaneously in X. So that is why these two examples are good to highlight that. Notice that this is not a closed set D01, the disk of radius 1 around 0. That's not a closed set in C. However, in this set X, this is going to be closed because its complement, which is D41, is an open set. So you have to first check that both D01 and D41 are open sets in X as well. And then the next observation would be that the complement of D01 is exactly equal to D41, which is an open set. And by the very definition, if the complement is open, our given set is closed. So D01 is closed in X, even though it is not closed in C. Similarly, in X prime, D01 bar is open, even though it is not open in C. In the metric space X prime, this is an open set. So you can actually sit down and check that if something is both closed and open and it's a proper subset of X, then it gives us a separation of our given metric space. So this is just rephrasing whatever we have just written above. Okay, so from your course on real analysis, you would have seen that the connected sets in the real line with respect to the standard metric, they are just intervals. So a subset X contained in R. So I am again suppressing the metric, it's the standard metric. is connected if and only if X is an interval. If you have not seen a proof of this, I'll refer you to Principles of Mathematical Analysis by Rudin. The proof is there in the second chapter. You can have a look. These are things which I am assuming because it's a part of our first course on real analysis, and we will be assuming a course on real analysis while we do this course. So here we have given a characterization of how the connected sets in R behave. We will not be able to give this kind of a characterization on the complex plane. However, we'll give an alternate description of how connected open sets in C will look like, or how they will behave. Before that, let me just prove a proposition for you. The proposition tells us how connectedness is behaving under continuous maps. So let f from x to y be a continuous function between metric spaces. Then f of x, the image of x, is connected if x is connected. So continuous functions preserve connectedness, the notion of connectedness. The proof is actually quite straightforward. Proof is by contradiction. Suppose, so let z be equal to f of x. Okay, so when we say that f of x is connected, we are going to say that z is connected. What we mean is that z, remember, is sitting inside y. We will be borrowing the metric from y by restricting it to z, and then treat z with the restricted metric as a metric space. When we say that z is a connected metric space, we basically mean that z with the restricted metric is a connected metric space. Okay, let's prove it by contradiction. Suppose z is not connected. That means there is a separation of x. Then let z be equal to A union B, where A and B are open sets in X. In Z, A and B are non-empty. And A intersected with B is empty. So this is the definition of separation. Okay, I'll just make a claim here that F inverse of A and F inverse of B are open in capital X, and not elaborate on it. Just observe that this follows since A is U intersected with Z for U open in Y, and F inverse of U is the same as F inverse of A. And because F is a continuous mapping from X to Y, it will be a continuous mapping from X to Z. This is the broad idea in establishing this particular claim, but let me not go deeper into it. I'll allow you to sit down and write down the details. So if we do accede that F inverse of A and F inverse of B are open in X, we also know that A and B are non-empty and F is surjective onto Z, using the fact that A and B both are non-empty and F is surjective and A comma B are non-empty. This together tells us that F inverse of A and F inverse of B are non-empty. So we now have non-empty open sets. Also, since A union B is equal to Z and F is surjective onto Z, F inverse of A union F inverse of B is equal to X. The only thing to finally check is that these are disjoint, which you should sit down and check. This follows directly because A and B are disjoint. So if we start off with a separation A comma B of Z, then we end up with a separation of X. But we started off with X, which is connected. This is the assumption in the hypothesis, right? This is a contradiction. So also let me just note this. And hence X is not connected. There is a separation, which is a contradiction. So that means our assumption to begin with was false. The assumption that there is a separation of Z. Hence, there does not exist any separation of Z, and therefore Z is connected. That's what we had set out to prove, right? Okay. Let me now define what is meant by a path in a metric space. A path from a point X to Y in a metric space is just a continuous map from closed interval 0, 1 into the metric space X, such that f of 0 is X and f of 1 is Y. So let me define that. A path in a metric space from a point X in capital X to Y in capital Y is a continuous mapping gamma from closed 0, 1 into X, such that f of 0 is X and f of 1 is Y. Not f, gamma of 0 is X and gamma of 1 is equal to Y. So geometrically, let's try to draw some paths in the complex plane. Suppose we have the unit disk. If you look at, say, gamma of t to be equal to delta times, so let's call this Z, t times Z from 0, 1 to C. This is going to be a path which starts at 0 and which ends at Z. So this is exactly the straight line which is being captured here. Well, I am sure you can sit down and construct very complicated paths by looking at various continuous mappings from 0, 1 into X. But my intention here is to get your focus on the following aspect. Suppose you have a path from, say, Z to W. Let's say there is a path like this from Z to W, and let's call this, say, gamma 1. And suppose there is a path now from Z to, say, zeta, and let's call this gamma 2. And if you traverse around or along gamma 1 till W and then along gamma 2 till zeta, then effectively we will be getting hold of a path from Z to zeta, isn't it? Even though I just said something which is sounding heuristic, it can be made precise, and this is what is commonly captured by concatenating two paths. So if sigma of S is defined as, okay, the context should be written down first. Let gamma 1 be a path from X to Y and gamma 2 be a path from Y to, say, Z in a metric space capital X. Let's define a new path, gamma 1 dot gamma 2, or maybe let's just call it something else, sigma of S to be equal to gamma 1 of 2 times S, where S is going from 0 to half. And in the second half, that is what we were doing, right? In the first half, it will go till W, and in the second half, it will go from W to zeta in the picture. Here, it will be from X to Y, and then the second half will be 2S minus 1, where S is from half to 1. By using the pasting lemma or by brute force, you can check that sigma is actually a continuous mapping from 0, 1 into X. Then sigma is a continuous mapping from 0, 1 to capital X, and moreover, sigma of 0 will turn out to be gamma 1 of 0, which is equal to X, and sigma of 1, if you check, it will be gamma 2 of 1, because S is now here, and it will be 2 minus 1, so gamma 2 of 1, which is equal to Z. So we get hold of a path now from X to Z. Okay. Let's now give an alternate characterization of how open connected sets are in C in terms of paths, or using the notion of paths which we just defined. So let me write it down as a theorem. A subset, an open subset, omega contained in C is connected if and only if there exists a path for every pair of points, if and only for Z comma W in omega there exists a path from Z to W. For any such pair of points Z comma W, we will be able to get hold of a path from Z to W if omega is connected. And if we can do that for every such pair of points, then omega will be connected. Let's give a proof of this theorem. Let's prove this direction first. If there exists a pair of points, if there exists a path between any two pair of points, let's prove that omega is connected. Again, the proof will go by contradiction like in the previous two cases. Suppose omega is not connected, is separated. We will get hold of a couple of points which cannot be connected by path, or suppose we have we will get hold of we'll arrive at a contradiction on something. We'll see what the contradiction is going to be. Suppose it is separated, then we can write omega as being equal to, let's say, U union V. Suppose you can write it as U union V, where U and V are both open in omega. Notice that omega is an open subset of C, so we don't have to worry about whether it is open in omega or whether it is open in C. But anyway, let's pick 2 points, Z and W, where Z is in U and W is in V. Okay, let Z be a point in U. Because it's non-empty, there certainly exists one such point, and W in capital V. So let's take 2 such points, Z and W. If we can get hold of a path, we will show that there does not exist a path from Z to W. And that's the contradiction we will be showing. If there exists a path gamma from Z to W, then gamma is a continuous map from 0, 1 to X, such that gamma of 0 is Z and gamma of 1 is equal to W. Then what we will do is, I'll just write the following and leave it at that. Then 0, 1 is equal to F inverse of U union F inverse of, it's not F, right, it's gamma. Gamma inverse of U union gamma inverse of V. And because U and V are open, gamma inverse of U will be open in 0, 1, it's a continuous map. Gamma inverse of V will be open in 0, 1 again, 0 belongs to this, 1 belongs to this, and they will be disjoint because U and V are disjoint to begin with. So what is this? This is giving us a separation of 0, 1. We know that intervals are precisely the connected subsets of R. There does not exist a separation of 0, 1, which is a contradiction. This basically is a contradiction. Therefore, hence, there does not exist a separation of omega, which is the same as saying that omega is connected. So one side was quite easy. The backward direction was quite easy. We will prove that if it is connected, if omega is connected, we will prove that between any 2 points there always exists a path. Okay, so let us assume now that omega is connected. Let's fix some point z0 in omega. Fix a point z0 in omega. And let's capture in the set A is defined to be all those elements in omega which can be connected by a path to z0. Let z be, let this be the collection of all those points z in omega such that there exists a path from z0 to omega to z. We will prove that this particular set A is both open and closed in omega. Let's first prove that it is open. So the first claim is that A is open. Both the proofs actually are similar. So let's first prove that it is open. Let z0 be some, okay, z0 is already taken. Let z be some point in capital A. We will show that z is an interior point of A. Okay, so to do that, remember that omega to begin with was an open set. Since omega is open, there exists some R such that dzr is contained in omega. This much we can certainly say. The fact that z belongs to A tells us that there exists a path from z0 to z. Now, since z belongs to A, there exists, what was A? A was the collection of all those points which had a path from z0. This is our A, right? There exists a path from z0 to z. Since z is in A, there exists a path gamma from z0 to z. If you look at the disk of radius r around z in the complex plane, that is contained in omega because omega is an open set. We certainly have one such r, right? Now, for any point for any w in dzr, consider this particular path. Consider the path. What do we call it? Sigma, or maybe gamma prime. Gamma prime is not a good one. Gamma 1 from 0, 1 to in fact omega, given by gamma of s is equal to, it's a path which I want to start from z and which ends at w. So it will be 1 minus s times w plus s times At 0 this should be z, so this is going to be 1 minus s times z plus s times w. And check that this is a straight line path which connects z to w, and therefore it's contained in dzr. So this hence is into C. That's certainly true, right? Gamma 1. And by the previous observation, define sigma to be equal to gamma dot gamma 1, or in the similar manner we defined earlier, this is gamma of 2s if s is in 0 half, and gamma 1 of 2s minus 1 if s is from half to 1, and this path sigma of s is a path from z0 to w, isn't it? And this tells us that w belongs to capital A, because A was the collection of all those points which had a path from z0 to that particular point, right? And the point W was arbitrarily picked in the disk of radius r around z. So this gives us that dzr is contained in A. And our choice of z was arbitrary, which hence tells us that A is open, because this is the very definition of a set being open. So we have established this particular claim, which tells that our set A is an open set. A very similar argument will tell us that A is closed as well. A is closed. To show that A is closed, we will show that omega minus A is open. So let again Z be in omega minus A. Because it is, and since omega is open, we can get hold of, we have Z, we have r greater than 0 such that dzr is contained in omega. If there exists, if dzr intersected with capital A is not empty, suppose this is a non-empty set, then there exists w in the intersection, and I'll just say that by a very similar argument above, we will be able to get hold of a path from z0 to z through w, and that would give a contradiction to the fact that z, or claim assumption that z is not in A. This would give a path, just fill in the details, we have already done that, give a path from z to z0 to z, contradicting our assumption that z is not in, z is in omega minus A, and therefore there does not, so the assumption has to be wrong, hence this assumption has to be wrong. Yeah, I was looking for where the assumption is written. This assumption has to be wrong, hence dzr intersected with A is empty, but that implies that omega minus A is closed. Oh sorry, omega minus A is open, because every point in omega minus A is now an interior point, and this implies that A is closed. We have now come to the alternate characterization which we have just written here. We have now got hold of a set which is both open and closed. So this cannot happen, but we have not, again this tells us, hence A is both open and closed, so hence A cannot be proper, therefore either A is equal to omega or A is empty. One of the two conditions is forced. But A cannot be empty because Z0 already belongs to A. Since Z0 belongs to A is not empty, which implies that A is equal to omega. And that's precisely telling that every point in omega can be connected to Z0 by a path. But again, by a very similar argument of concatenating paths, any 2 points can be connected now by a path through Z0. Thus, by let me not elaborate, any pair of points in A can be connected by a path. Therefore, we have now a characterization of connected open sets. Remember that we have used the fact that omega is open when we proved which was the direction, the forward direction. We first proved the backward direction and then we proved this forward direction. In the forward direction, we have indeed used the fact that omega is open in the proof. So we have now a characterization of connected open sets in the complex plane as being those open sets such that any 2 points can be connected by a path. Okay, let me not go more into the notion of connectedness. We will develop any notion of connectedness which is needed and which you might not be familiar with whenever it comes, as and when it comes.